Okay, so today we will talk about two things. One is actually the spectral representations. Okay, another thing we want to talk about is the isotropic U surface. Okay, so these two items. Let me talk about the first item first, the spectral basis. So let's say I have a stress. Okay, so typically we write the stress as a symmetric tensor. Now we can write sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 2, sigma 2 3, sigma 3 3. That's it. Okay. Why is that? I don't write the other half. It's because Cauchy stress is a symmetric tensor. So I just write SYM here to represent that sigma 1 2 equal to sigma 2 1, sigma 3 2 equals to sigma 2 3, and sigma 3 1 equal to sigma 1 3. Okay?
Maybe a dumb question, but is there a case where the stress is not symmetric?
Yes, that's an excellent question. So Cauchy stress is symmetric because both of the bases is in the deformed configurations. There are stress that are defined in different way. If you look at the stress in details, in Cauchy stress particular, we would write sigma ij times sigma ij is actually the component of the stress, is not the stress, and we will write ni times nj. Okay, so this one give you the second item give you the type of the mode of the stress. Okay, you can think about it as a mode. And then the first one give you the sense of magnitude. Okay. So now the stress, Cauchy stress is symmetric just because you need to fulfill the balance of angular momentum. However, imagine that I want to represent the stress in the undeformed of the current force that I apply onto the undeformed configurations. Then I will break the symmetry. Example of that would be the first physical stress, Pij. Okay, if I write the first physical stress, I will write it as a P. P is actually equal to Pij. Notice that I use the capital letter J to represent the reference configurations, and I would actually write something like this. Sorry. Okay, if you look at Hosafo book, what they would like to do is to use the capital letter for the undeformed configurations and the non-capitalized letter for the deformed configurations. What is n and n? So n is actually the basis expressed in the undeformed configurations, and n is actually the vector system or coordinate system that are expressed in the deformed configurations. Okay, now there are stress that are also symmetric, but in a reference configuration, for example, the S, the second critical stress. Now here, let me go back to this. Okay, for simplicity, I will focus on the U stress that are weakened in terms of the Cauchy stress that is symmetric. Now, what is special about the symmetric tensor? Symmetric tensor actually have eigenvalues of eigenvalue and eigenvector, and the eigenvector in particular have a very important property, and that is the left eigenvector and the right eigenvector are identical, and hence they are simply called eigenvector. For non-symmetric tensor, the left and right eigenvector are actually different. Okay, this is also important. You can see it here. Okay. And now let's go back to this. Now, if I want to represent the stress, okay, one choice I have is that I write down all the stress component in some coordinate system. And in some literature, I would actually write x1, x2, x3, just to remind people that this matrix is used to represent the stress component in the x1, x2, x3 coordinate system. Now, there are other ways to actually represent the data, the stress in a more economical way. In particular, we want to actually compress the data in a sense, compressing the data and actually separate the mole and magnitude. We would oftentimes use the spectral decomposition. So spectral kind of, if you see the word spectral in mathematics, usually they are related to some kind of decompositions, in particular eigenvalue decompositions. In our case, this is exactly like that. So to represent the stress in the spectral directions, I would simply have the opportunity to split the magnitude and the mole or the directions. And then I will have two types of representations. One is called the principal values, or in this case, if this is just the stress, the principal stress, which is sigma 1, sigma 2, and sigma 3. Okay, you learned it from the undergrad linear algebra, right? Okay, how do you let me ask again, how to compute the eigenvalues for 3x3 matrix? Okay, I think I asked many times. Take a determinant of the sigma minus lambda I, and then what that will give you a characteristic polynomial, solve the characteristic polynomial, and then you will get the eigenvalue. Now, there's another thing, which is actually the eigenvector. In this case, I'll simply call it principal directions. Okay, so is principal directions eigenvector? They are actually eigenvector, and because there are 3 eigenvalues, they are corresponding 3 eigenvector. N1, N2, and N3. Okay, 3 eigenvector. Does that make sense? And they have very specific property. Those N1, N2, N3, they are orthogonal to each other. So what does that mean by being orthogonal to each other? It means that they are 90 degrees apart, and the 90 degrees are actually separated in different dimensions, okay? N1, N2, okay, N1, N2, N3. Okay, so any 2 vector combined will span R2 space, any 3 vector that when we would span a volume, okay? You understand what I'm saying? Okay. So why do we care about the eigenvector? It turned out that I can write the stress in a spectral form that looks like this. Okay, and what is M? M is actually equals to MA is actually equals to NA times NA. Okay, does that make sense? So if I write it in great details, let me add another page. So sigma equals to this. Now this is the tensor format. If the individual component can be written as this. and M ija is actually equal to NIA. Okay, so A just can't. So do you know what is this summation label? Do you know what is the meaning of this? Okay, if I write it in detail, that would be just sigma A, sorry, that would be sigma 1 M1 plus sigma 2 M2 plus sigma 3 M3. Okay, does that make sense? Okay, so let me use some example, okay, just to motivate the discussions, okay? So, okay, do you think that would be better? So far, how many of you are with me? Okay, okay, maybe I don't need the example, or are you all with me? Okay. Now, let's consider a case, okay? Maybe not necessary example. Now you imagine there's a cylindrical object, and then I push stress, but then they are actually equal in the magnitude in the radial directions. So sigma 1 equal to sigma 2 in the radial direction. And then in the vertical load, I apply a slightly less force to give us a sigma 3. Okay, how do I express this stress? Okay, so how do I expressing this? Now, what are the eigenvalues? The eigenvalue is sigma 1, sigma 2, sigma 3, or sigma 1, sigma 1, sigma 3. Does that make sense? Okay, what is eigenvector? Well, they're infinite eigenvector, but the one that with unit 1 are simply what? 1, 0, 0, okay? Does that make sense? M1 equal to 1, 0, 0 if I establish x1 here, x2 here, and x3 here. Okay, M1 equals to 1, 0, 0, N2 equals to 0, 1, 0, and N3 equal to 0, 0, 1. Okay, do you get this part? Okay, does that make sense? So what will be the stress in the spectral form? Well, first of all, the stress itself, if I don't write it in spectral form, what would that be? That would be simply sigma 1, sigma 1, sigma 3, 0, 0, 0, 0, 0, 0. Okay, does that make sense? Okay, I don't see any shear in this particular example, so the order of diagonal term are actually 0. Now, if I want to write it in spectral form, so I would simply write this equal to, so the stress is actually expressed as the eigenvalue and then the principal directions or the spectral directions A. And in this case, that would be equal to what? That would be actually equal to sigma 1, M1. M1 is simply N1. Actually, maybe let me change the notation. N1 here, N2, N3. Okay. So M1 is actually equals to the tensor product of N1, N1, which is actually what? Which is actually, if I write it in detail, N1 for the first vector one, M1. Okay, and then what? N1, N2. Okay, and what is this? There is only one non-zero component, just 1, 0, 0, 0, 0, 0, 0, 0, 0. Okay, can you see that? Okay, because there's only one component. So if if I actually write Ni, Nj, so there's only one combination out of that Ni, Nj that are actually non-zero, and that is N1, N1, right? You understand what I mean? Sorry. You see what I mean? N1, N1 would be simply this term times this term. Okay, 1 times 1 is equal to 1, right? Okay, but N1, N2, 1 would be what? Would be the first term is still here, but then the second term is 0, so I get 0, okay? You get what I'm saying? So now go back to this. The expressions would be, let's see what M1 plus N2, M2. Okay, so that is something very interesting here because this is also equal to N1. So what you would end up have is actually N is actually sigma 1, M3, the third matrix, 0, 0, 1, the tensor product of it, plus the identity tensor equals to M3 sigma. Okay, do you get it? Do you get this part? Okay, let me write it out. Maybe that would be easier. What is identity tensor? That is 1, 1, 1, right? Okay. What is the minor M3? Is actually identity matrix. Is simply 1, 1, 1, right? And what is M3? Just like M1, the only non-zero term is the 3, 3 term, right? Isn't it? So you minor it, you get the first two term. Okay? So basically this term. Okay? You get it? So okay. So this is basically identity minus M3, right? Sorry. I think I need to make the notation more. And the third spectral directions. Okay, not the component. Sorry, M. Okay, sorry, you get it?
Plus, so plus sigma 3 and 3, right?
Sorry, can you say it again?
So it's equal to sigma 1 minus M3 plus I.
No, minus M3 plus I, yes.
Then plus sigma 3, right?
Oh yeah, plus sigma 3, yeah, you're right.
Okay.
Sorry, not equal to, yeah, sorry. Yeah, okay, sorry, I know what is the confusions. You add it together, okay, sorry. So let me give another example, okay? So what if you load something hydrostatically? Hydrostatically mean that you have a sigma 1, you have sigma 2, you also have sigma 3, but sigma 3 equal to sigma 2 equal to sigma 1, sigma 3 equal to sigma 2 equal to sigma 3 equal to sigma 1, sigma 1 equal to sigma 2 equal to sigma 3. Okay, can you think about an example where the material are low hydrostatically? Okay, when you apply pressure, when you apply air pressure on a material, okay, you can kind of idealize it as the material subject to hydrostatic stress, air pressure, okay, for example, like the surface on a basketball, okay? So in this case, what is the spectral form? The spectral form, the sigma in this case would actually be just diagonal matrix, diagonal tensor, right? Right, isn't it? Okay, and we simply would have the what is the spectral directions in this case? What is the difference between the spectral direction in the previous case and this case? Yeah, it will be the same because you just need to span the space with the same basis vector. There is no shear to actually force you to change directions. Now, there is a very important theory on the um, on the spectral directions. If I add all the spectral mode or spectral direction together, I should get back the identity matrix. Okay, in this particular case. Okay, however, in a more general sense, N1, the same matrix, the same set of the principal directions, if you have a dot product together, they should equal to 1. Okay, why is that? Well, because you can have infinite eigenvector, but if you don't normalizing it, then you are not really representing a direction, right? Okay, you see what I mean? Do you understand what I'm saying? So you can have a basis. Let me use a vector as an analog. Okay, you can describe this. Let's say this is an A matrix. Okay, and this is actually an N matrix. N matrix. Sorry, this is an A vector and this is an N vector. And N vector, the norm is equal to 1. And A matrix and A vector, the norm is actually not equal to 1, maybe equals to 2. For example, you can use both vector to represent this quality, okay, this vector. But then if you're actually using this as a basis, you would actually just put the ratio to describe that vector, and then that ratio, the coefficient for this vector is not representing the magnitude. You understand what I mean? Now, this is actually important when we actually want to describe isotropic functions. Okay, what is isotropic? What is the meaning of isotropic? Do you remember? What is the meaning of anisotropic? Okay, a stack of the paper. If I actually have the paper stacked together, are they isotropic? They are not isotropic. Why? Because if I actually apply shear in these directions, the paper would actually snap like this, right? There's a frictions between the paper that give you the deformed shape. Versus if I actually apply the loading in these directions, okay, what happened to the paper? It may buckle, right? Okay, so for different orientation, you get this different response. Those are not isotropic. Okay, you get the idea of isotropic behavior. Okay, for U functions, they can also be isotropic and anisotropic. And one thing that are actually important for U surface to be isotropic is that they can be used to model material that yield in an isotropic way. Why is that? Let's consider not the J2 positivity, but consider a very general case where we write U functions for a fixed internal variable as a function of Cauchy stress. Okay. Now, in general, what we actually want is that if I change the coordinate system, they are equal to each other. Does that make sense? Okay, so what is Q? Q is actually a rotations. Okay, it could be any rotations, like rotations in the special orthogonal group of 3 in particular in the physical space, special orthogonal group. So eigenvector, for example, they always appear in an orthogonal manner, but they are not special unless you're normalizing them, okay? So I want to write a stress functions that actually fulfilling this criteria, okay? So now before I answer that questions, I want to talk about the U function that doesn't fulfill that criteria. What is that? Can you give an example where it doesn't work? What about the U function? Go to 2 minus 10, okay? Would it work? Okay, would it work? It won't work. Why is that? Well, I mean, it won't work in the sense that they are not isotropic, okay? But why is that?
Well, once it can be changed, like in different coordinate systems.
Yeah, I only give you one component of the entire matrix, and then so by itself, I actually either doesn't have the information of what happened to what if I don't know, what if I never load the material in 1, 2 direction, but in 2, 3, I will also get a shear, right? Does that mean that it will never yield? Okay, because sigma 2, 3 is not even in that functions, right? Okay, so what is the limit for sigma 2, 3? Do I know that? I don't even know from that equations, right? Okay, you understand what I mean? So you can argue that it's actually a criteria, but it's either incomplete criteria or is at least incomplete criteria if it's actually it's not even an isotropic criteria, right? You see what I mean? Now there are other choice to write it that would actually make it very clear is that, and this is actually why we need the spectral decomposition. What if I write the stress? Okay, so I have this matrix, and then I actually let me change apply the rotations to the left and right directions. Okay, so what happened is that I would create a new stress that actually with a change of the observer, and then I will write NA times Q dot NA. Okay, so what will happen to that? Okay, what is QNA? Okay, so N is a unit vector, right? Okay, so this is a vector that, let's say this is NA. I actually just project it into the surface onto the plane. Okay, and then NA as a norm equals to 1. Maybe if I take the norm, I get 1, right? Okay, so what is the meaning of the rotation times the NA? Okay, I simply rotate it, right? And then I preserve the length. So the new N vector, okay, would be equals to Q dot NA, and the new vector that I actually now put the overhead there would also have a norm equal to 1. Okay, does that make sense? Okay, so the same thing for this part and this part. So I would end up I would simply have NA equals to NA times NA. Now this overhead with the overhead N and the original N, okay, what are the relationship between them? By itself, they don't have any correlations, but they are actually simply two set of vectors that span the same space. So this could be N1. Let me use the classical notation. This could be n1, n2, and n3. So I need to practice my notations. n1, n2, and n3. And the new one would be simply rotated versions of them, maybe something like this. And then n1, n2, and n3. Okay, so they are rotated. Does that make sense? Now, this is actually interesting because, as you can see, if this one, if the original stress and the rotation stress, they equal to each other. So let me take this out. Okay, what does that mean? That means that the stress, the U surface, in fact, doesn't depend on the eigenvector, right? Okay, does that mean, do you understand what I'm saying? If I can write the U functions, that actually satisfy this criteria, okay? You understand what I'm saying? If I can make the U functions such that I write it in such a way that the U functions, if I actually apply the rotations of the stress component on the left and right hand side, I get back the original U functions values, then what it actually means is that the stress is actually isotropic in the sense that it's not sensitive to rotations, okay? So we change from the behavior that like a stack of paper to something like a tofu or whatever, that or rubber that appear to be more isotropic. Okay, so in this case, I will reduce the stress as functions that only depends on the eigenvalue but not the eigenvector. Okay, does that make sense? Now, if I write it in, but you can think about it as a way to simplify the expressions of the yield functions, but they are concurrently restrict the material you can model. Okay, you understand what I mean? It makes it simpler because initially, what is the dimension of the yield functions? There are 6 input, right? Because there's a 6 non-zero component. There are 6 not necessarily non-zero. There are 6 independent components in the Cauchy stress tensor, but now I actually reduce to 3 inputs, right? There are 3 individual inputs, just the eigenvalues for 3 by 3 matrix, okay? So I make the problem easier. In exchange, I cannot model any anisotropic material anymore. Okay, you see the trade-off? Just like the J2, I actually reduce the 6-dimension problem into the, I actually reduce the 6-dimensional problem into a 3-dimensional problem in this particular case. But in exchange, I cannot model anything anisotropic, which is actually a generalization of the J2, because in J2, I reduce the 6 dimension to 1 dimension. I cannot even measure anything that are pressure sensitive, right? Okay, so now notice that in this particular case, stress can be written as sigma 1, sigma 2, and sigma 3 for isotropic material, or for isotropic U surface. More accurately, let me put it this way. And the order doesn't matter, okay? You can switch the order, whatever, because they're eigenvalues, okay? Now, there are more than one way to write the isotropic functions. Another thing we learn from matrix is that sometimes people like to write it in terms of invariance, n1, n2, and n3. I'm sorry, I1, I2, and I3. I are not identity matrix, or in here, in this particular context, they are scalar invariance, okay? So who know what is the first, second, and third invariance? No one know? Okay, so, okay, let me give a little refreshment for your linear algebra course. Okay, what is invariance? Okay, we get the invariance from something that I talk about many times. Just have sigma minus just have the compute the eigenvalues, use it by actually try to obtain the characteristic polynomial. So this is simply the determinant of sigma stress minus the sigma component identity. So this one is just or maybe lambda. Just try to not confuse you. And then I'll just basically write lambda. Okay, you recall this? Hopefully this is not new for you. And then if I do it, how do I actually solve this problem? Okay. Do you know how to compute a determinant? How many of you know how to compute a determinant? Okay, so let me refresh the idea. Okay, you put a plus. Okay, let me do it very slowly. You put a plus sign here, minus here, plus here. Okay, why do I do that? Okay, I'll have this term, and then I compute the cofactor. Okay, and then I have this term times the things with this cofactor, etc., etc. If I'm not going to do it in details. You can review it yourself. If I actually obtain the, if I add those expressions together from the cofactor, then what I will have is sigma 3, sorry, lambda minus I1 cubic, sorry, square, plus I2 lambda minus I3 equal to 0. Okay, this has a very specific name. It's actually called the characteristic polynomial. Okay, and what is the invariance? Is just the coefficients of this characteristic polynomial, and they actually have a very specific number. I1 is simply the eigenvalue add together, and I2 is simply sigma 1, 2, sigma 1 times sigma 2 plus sigma 2 times sigma 3 plus sigma 1 times sigma 3, and I3 is actually equal to sigma 1 times sigma 2 times sigma 3. Okay, so far so good. So one thing that actually very important is that I1, I2, I3, they are functions of only the eigenvalues, but not the eigenvector. Okay, so if you ask one of my students that are about to defense, he will tell you that if you need an isotropic material, you need to put some structural tensor and create more invariance. Strictly speaking, they are very different. The first three invariant has a very important mathematical foundation in the sense that they're the coefficients of the characteristic polynomial, and I1, I2, I3 are identical no matter how you rotate the stress. Okay, do you see that? Why is that?
Because no matter how you rotate the tensor, the characteristic equation should be.
Yeah, exactly. And why is that?
Because eigenvalue should be same.
And because the eigenvalue are independent of the coordinate system you're expressing it. Okay. Okay, so this is actually a good way you can. Why is the eigenvalues give you a sense of magnitude? This is actually why. Okay, so because no matter how I change the coordinate system, they share the same value. The value is unchanged regardless of the orientations. Okay, so so far so good. Now then the next question is harder. Okay, if I express the stress in the spectral decompositions or spectral representations, how do I represent the change? Okay, you understand what I'm saying? Let's say stress is equal to the eigenvalues times the spectral directions. Okay, now I want to change the stress. Okay, the stress is changing. Okay, now how do I actually represent the change? Okay, how do I represent the change? Now you need to think about it in a very precise way because you're dealing with two very different entities in these representations. The first one is the eigenvalue. Of course, if I change the eigenvalue, I would actually introduce change, isn't it? Okay, so I can changing it by introducing this not equal to 0. That would lead to change, right? Now the second one is actually more interesting. What happens if MA is changing? The spectral direction is changing. How do I correctly changing MA? Okay. Does anyone know how? How is M change? Okay. Now you need to think about what is M. M is actually the spectral directions, and they are actually the tensor product of the principal directions. So how do I change the directions? Okay, not change the magnitude. If I want to change my directions, okay, let's say you go to south. Okay, you want to leave Columbia and maybe go down to the downtown or okay, World Trade Center, whatever. I need to go down, right? I need to have the magnitude, need to have the footstep. I also need to go to the right direction. How do you change the directions?
By changing the rotation.
Yeah, by rotating it, okay? So how does the rotation change? Okay, so this is actually the topic. I want to able to express the change of this, okay? Why do we care about the change of this? Of the stress. We need to write the stress update algorithm, right? Without able to write it, the change, then I actually cannot to talk about. Now, let's consider a coordinate system x2, x3, and x1. Okay, they are separated by 90 degrees, and we call it orthogonal. Now, I actually want to changing it, so I would actually have a new vector that are rotated from the old vector n. Then for the argument, I'll just write it down in details. So Q are actually identical. They are actually second order tensor that map the reference n vector to the current non-capitalized n vector. Okay. So in order to do that, I have a very important task. These rotations cannot change the magnitude of n and m in the sense that the norm of n, small n, and the big N need to be identical and equal to 1, right? Okay. Now, how do I do that? I simply need to restrict the Q to be something very special. The dot product of Q and then the transpose of Q has to be equal to identity. Okay, which we actually hopefully I talk about that before, which actually lead to the fact that the transpose of T is actually equal to Q minus 1. Okay, that's why in your undergrad school you will see sine, cosine, minor, sine, cosine, 0, 0, 0, 0, 1, something like that. Okay, why do we use sine and cosine? Okay, there's a beauty on that is that sine square plus cosine square equal to 1. Okay, so let me take this out. Okay, now let's think about it from these equations. Okay, so how do I change the rotations? Okay, so let's apply a dot product to it, shall we? Okay, so if I take a time derivative from both sides of this, what would I get? Okay, what would I get on the right hand side? 0, its identity. Okay, or change, it doesn't change in time, no change, 0. Okay, I get a 0 matrix. What happened to the right hand side? Okay, so I would apply the chain rules, hopefully, which actually give me Q plus Q dot times QT. Okay, does that make sense? The dot is just the time derivative. Okay, I apply it on the second term and in the first term while I keep the other term together. Okay, what is the interesting thing about this? Is that if I put it onto the other side, I get Q dot times Q dot T equals to minus Q dot QT. Okay, do you see anything special here? Do you see anything interesting here? Not really. Okay. How about this? Sorry. How about this? Do you see anything interesting here? They are skew symmetric tensor, right? Isn't it? Okay, so this is actually often called a spin tensor. And this one is actually the transpose of the spin tensor, which is actually equals to the negative of the spin tensor. Okay? You see that? Okay. So the change of the rotations, interestingly, can be characterized by the spin tensor, and spin tensor is actually not equals to Q dot. Okay? Do you see that? That's very important. Okay, normally in a classical vector, if I actually want to, let's say I want to see how x is changing over time, I'll take the time derivative, that's it, right? Okay, here you would actually represent the change of the orientations using the spin tensor. Okay, and this is actually one thing that are very important in group theory. Spin tensor is actually the Lie algebra of the rotation group, okay, which is actually the Lie group. Okay, so each Lie group have a Lie algebra, and then the Lie algebra allow you to actually perform operation and represent change of the things that are in the Lie group. Okay, you see what I mean? So you may not able to directly capture the change of the Lie group using the vector language or the classical Euclidean language, but you may able to actually map it into a spin tensor, and then that will allow you to do it. Okay, let me give an example. I want to represent the change of the n vector, which is a normal vector. The reason we need to deal with that is because n is not an arbitrary vector in the Euclidean space. N has a property. N has to be equal, have the represent orthogonal directions. Na itself has to be able to span a volume. Okay, in this particular case, n1, n2, n3 has to be orthogonal to each other, and n has to have the magnitude of equal to 1, individual n vector. So now Na is actually equals to Q dot Na. Okay, but it's actually also equals to the Q dot Q minus 1 Na. and that is also equals to the q dot qt, because it's actually the transpose is equal to the inverse, and that is actually equal to the spin tensor times the transpose of the spin tensor times NA. Okay, so this is actually the important thing. N dot A, okay, the change of the normal vector in the for the Cauchy stress spaces for example is equal to the transpose of the spin vector times the NA. Or what is the other way to write it? Yeah, I can also put NA W, but what would be the difference? I need to put the minus sign, right? Okay, why is that? Because W is actually minus WT. Okay. Okay, so is it very boring? Maybe a little bit. Okay, but no problem. Actually, what we actually want to do is the following. We need to build that entity so that we go back to the original algorithm. Okay. Let's see. So there are something that could be also helpful hints on that is that NA and the rate of change of the NA are always orthogonal to each other. Okay, why is that? Well, you cannot represent any change if you actually talk about the same direction, right? Okay, but let's also proving it mathematically. Do you know what I'm doing? Do you know why I want to prove the NA and N dot A are orthogonal to each other? This means orthogonal. Then I try to compute this quality. Okay, why is that? Because if two vectors have a dot product that are equal to 0, that means they are orthogonal to each other, right? Think about 1, 0 and 0, 1. Okay, you have a dot product equal to 0. Now, this one is actually equals to NA. Okay, just using the notations I have before, and that is also equals to the, let me see, and is actually also equals to the NA dot WT dot NA, which actually is also equals to the minor AW dot A. Okay, so if you actually look at it, if you actually look at the term, you would actually find out that the two terms cancel each other, and then I would actually have 0. Okay. Now, there are implications to that in the sense that so there's an n dot a, and then if I write it in the spin term, I'll have WBA and B plus WCA and C, and that is equals to the summations of B not equals to A times BA and B. Okay, so why do I write it in this particular case? Why there is no WAA, WBB, WCC? Okay, does anyone see that? I omit that, right? When I write the spin.
It's like the diagonal terms are 0.
Yeah, the diagonal term is 0, okay? And then the spin in the same direction. So N and N dot A are actually equal to, they are orthogonal to each other. Okay, just think about it in a graphical way. Okay, if I draw it this way. So there's a NC. Okay, and then I actually, if I want to changing it, then we have N dot A that represent actually a vector. Okay. So far so good. Let me see. Okay, so let me show it in greater details about what we talk about. So let's say that we have A double dot B equal to 0. Okay, and A is actually a symmetric tensor, and B is actually a skew symmetric tensor. Okay, by definition, the symmetric tensor would actually have the transpose equal to each other, just like the Cauchy stress. On the other hand, tensor like spin tensor would be skew symmetric, which means that they would be actually the off diagonal term are of the same magnitude but opposite to each other. Now, what happened to this? I want to show that the symmetric part, the scalar product of the symmetric tensor and skew symmetric tensor are actually always equal to 0. Okay, so let me write it in details. So in Einstein notations, we have the A, IJ, B, IJ, right? Okay. So to express this, okay? And so what will happen to the symmetric tensor? If we write it in details, what I would have is that I will have 1/2 of Aij plus Aji. Okay, do you know why I write it in this way? This is by definition being symmetric, right? Okay, so if I take a transpose, because the transpose and the original tensor are identical to each other, if I take a half of them and then add it back together, you get back the original thing, right? Okay. Now, what does this give us is that 1/2 of the Aij, Bij plus Aji, Bij. Okay, so Aij, Bij is equal to this quality. Okay, and this is equal to 0. Why? Because B is a skew symmetric tensor. So if I want to switch, if I want to re-expressing them, B, I can actually take a transpose of B and I will get Aji, Bji. Okay, but instead of having a positive, I have a negative number, And these two physical quality, even though I purposely write it in a reverse index, they are actually the same thing. Okay, can you see that? Because the first index and the second index, dummy index, the location are in the same locations. Okay, that's not a good practice in general. So but I just want to write it in these particular details, and that is equal to 0. Okay, so important lesson that we have there is that a symmetric tensor and a skew symmetric tensor, if I actually have a scalar product, that actually equal to 0. Now go back to this. This would actually explain why we would actually have the dot change it. N dot a times n a would be equals to 0. Okay, now then let us start to write the expressions for the stress changes. In general, I will write the stress change like this to indicate is the time derivative of the Cauchy stress. Let's say the stress itself. So let me do the color. Let me add the right color here. Okay. Let's say that I have a stress that are expressed in spectral form. Okay, now I actually want to write the the waveform. Okay, so sigma dot is actually now equals to the time derivative over this one term, second term, and three term. Okay, so that three term there, if I apply the chain rule, what I would get is actually sigma a dot times n a. This is actually corresponding to the first term. Does that make sense? This term taking a derivative. Now then I move to the second term. That would be equals to the time derivative of na times na also. And then I would also have one more term, right? What is the other term? Okay, so does that make sense? Okay. So what happened here? Okay, is there any way I can make it simpler? So what should I do here? I have these three terms, right? But anyway, the first thing I would do is that I would basically rewrite this. Remember what is n dot a? N dot a is actually equal to the spin tensor times the Na itself, right? Okay, before I did that, let me substitute the what I have here. So what I would have is that I would have the sigma A. I would have the term that actually indicate the change of the eigenvalue given a fixed directions, which is the first term, plus the spin term W times sigma A minus sigma A dot W. Okay, do you see why? I just switched the order. Do you see that? I just switched the order. Okay, and when I switch the order, remember W is actually a skew symmetric tensor. Okay, so I would actually obtain my minus sign here. Okay. Now, typically we don't like to write it this way. We would like to write it in a more compact form, and recalling that the diagonal term and the off diagonal term, the scalar product of the two, are actually equal to 0. So what usually happens is that we will write it in this particular form. The first term remains the same. The change of the principal values corresponding to a fixed stress plus what we call the spin term. We will write the sigma 3. We would actually write the summation term, but we will actually add another summation term to say that we don't operate everywhere, but only when B and A are not equal to each other. And then we would actually write the spin term component like this. Okay. Does that make sense? Okay, this is sigma dot. The first term corresponding to the change of eigenvalue. The second term corresponding to the change of directions. Okay, does that make sense? Okay, now I want to put it into actions. Then what we actually need to think about is to how to rewrite what we learned from the J2, but now using the spectral form to write the constituted law. So I write the stress. Now every physical quantity would be represented by the eigen, would be actually represented in the spectral form. I will have this. I will write stress. I would also write a strain in this particular case. Now I want to ask you a questions. I write the spectral direction for the elastic strain and the elastic stress as identical, okay? So they actually share the same principal directions. Under what case would that be true? Okay, can you actually guarantee that if you have a stack of paper, or you actually have a crystal that have a lattice system? That would not be true, okay? So they share the same spectral directions only because the material is isotropic. Okay? Now, but you can kind of see that if they're isotropic, you do save a lot of time, isn't it? Okay, you don't have to think about the eigenvector for a while. You can actually throw it away and just concentrate on the eigenvalues, okay? Why do I say that? Because if I actually write it like this, then the eigenvalue and the eigenvector, they are directly related. In the case of linear elasticity, we can write a linear mapping. In particular, sigma A is just the summations of the A B E epsilon B E. Okay, what is this? Okay, so A is a free index. So A B E is actually kind of like an elasticity tensor, but only in the spectral form. Okay. So what is the dimension of this? This would be simply by a 3 by 3 matrix, isn't it? Now consider the case if my material is actually isotropic and linear, then the elasticity can be written in terms of the bulk modulus, a term times the shear modulus term. Okay, but in the case of AB, so what did I do? I don't know what I did, so let me put in. Okay, in the case of A, what I would have is that I can write this populate by only two scalar. And A is actually equal to K plus 4 nu divided by 3. And B is actually K minus 4 nu divided by 3. Okay, A also have another name that is actually called a one-dimensional modulus. Okay, why is it called a one-dimensional modulus? It's because if you confine the material and loading it only in 1D, this is exactly the elastic modulus for the confined 1D model where you restrict the radial direction to be not deformed. Now, in order to write it in incremental form, I need to introduce the spin term, and the stress-strain relationships are actually, the stress and strain algorithm written in the spectral directions, they are actually identical, almost. They have the spin term for the principal directions. They have the fixed term for the principal directions, and then they have the spin term. Okay. By the way, if you actually, I just want, before I actually go further, do you know what does that look like if I want to visualize NA times NA, the tensor product of it? If this is actually a component, how will it look like? Okay, if I actually have a cubic, and then I apply a deformations that look like this, NA, and N is one of the directions, N. Okay, so what will it look like? Okay, the cubic would actually become what? So it's the direction will become longer. Okay, this is actually what it looks like for the first time. That is actually the effect, right? Okay, it can be longer or shorter, but then it remain normal directions. What about this NA, NB? NA and NB are always orthogonal to each other. Okay, so if NA look like this, NB looks like this. Okay, they're 90 degrees apart, right? So what does that tell you? Okay, so if this term tell you the magnitude of this is actually kind of like shear, right? Okay, you see what I mean? So do you see the difference? If a uniaxial loading, you're not going to move the if you load the material in a uniaxial manner, okay, there's no shear. You're not going to change any principal direction. Does that make sense? Okay, a triaxial compaction test on an isotropic material never create any spin, right? Okay, but if it's shear, then what happened to the principal directions? If we shear the material, the principal direction is keep changing, right? Okay, you see what I mean? And hence you actually see the change of the rotations, okay? If you take out one of the term, then the waveform is completely wrong, okay? Does that make sense? I just want to explain a little bit of physics so that it's not so dry. Does that make sense? And so you can also see it here, okay? You can only trigger those things if sigma B and sigma A are not equal to each other, okay? Does that also make sense? Okay. Now the same thing is for the string, which is actually kind of boring, but for computers, I just write it down here. I again would consider the change of the elastic string into two different parts, the change of the eigenvalues and the change of the spin. That make the eigenvector change, while the eigenvalue is not necessarily changing. Sorry, there's no dot here. Okay, you see, the first term I changed the magnitude. The second term I did not change the magnitude at all, but I actually changed the directions. Okay. Can you guess why we want to write this? We write the stress and strain in elastic strain, right? Okay, how do I relate the stress strain together? How do I actually write related the stress with strain? Sorry, how do I relate the stress with the elastic strain? I use the elastic tangent modulus, and if the material is linear, then I only have one. Elastic tensor, right? And the elastic tensor are actually written in the following way: CE equals to okay, this is the first term, sorry, AB. Okay, why do I have two index here, A and B? And why is this a M tensor? Oh, sorry, why is it the spectral directions? Because I want the stress expressed in the spectral directions, the stress rate change equal to CE, not the CE dot, okay? CE double dot epsilon dot E, okay? So in order to map a second order tensor in order to create a mapping between two second order tensor, I need a fourth order tensor, okay? And I still have the principal term where I actually update the principal values, but I also need a second term. That tell me the spin. And that would be MAB times MAB plus MAB times MBA. Okay, so I still have the term where I change the eigenvalue, but I also have the term where I fix the eigenvalue of the stress and strain, but I actually provide a spin. Okay, now what is MAB? In the stress component, I never need to define what is MAB because I only have MA, I only need the MA. MAB is actually equals to NAI times NBJ. Okay, does that make sense? Okay, so now this look pretty painful so far. Okay, do you agree? It looks very complicated, right? So what is the benefit? Okay, the benefit is mainly on when we actually write the plasticity model. We don't necessarily directly need to do with that, but instead we actually have some benefit on actually writing our U surface only in a vector space instead of dealing with the tensor. Okay, let me finish this part. U surface. In principles. Okay, as we say before, here I would actually write sigma 2. I would create a space where it actually is spanned by the stress, in particular the principal stress. Okay, so for example, like what we talk about, what we previously do with the J2 plasticity, but now I want to actually define something a little bit more complicated. Any arbitrary shape in the principal stress space. So I would actually need to consider, let's say, for example, a cone. Okay, then what should I do? I need to write, instead of writing the stress only as a function of J2, I will write the stress as I will write the U surface as a combination of the internal variable and stress. I would actually reduce the form, restrict it to only sigma 1, sigma 2, sigma 3, and Kuiper. Okay, so for the moment, Kuiper is undefined. It just represents some kind of thing like what we learned from J2, the back stress, or the radius of the yield functions. Okay, it's just some parameter for us to manipulating the geometry of the yield stress. Okay, now if I want to do that, okay, then what gives us the flow rule? So the plastic strain rate is actually still equals to lambda dot times the stress gradient, right? Okay, is it true? Okay, now, but instead, what I actually want to write is the following. I want to leverage the fact that this is only depend on sigma 1, sigma 2, and sigma 3, and see whether I can actually write the ingredient or the stress ingredient in a simpler manner. Okay. So there, I think that the first thing I actually want to use the spectral representations is actually to compute the passing flow and the stress gradient. And let me assume an associative flow rule. In this case, I would actually written the stress gradient would be equal to FA times sigma A divided by the partial derivative of the sigma A with respect to the stress tensor. And FA is actually equal to the partial derivative of the U surface with respect to only the stress, principal stress. Okay? Okay, you see what I mean? Okay, so far so good. Now, this thing directly, if you want to using it directly, is not useful. So let's first figure out what is this. Do you know what is this? Okay, so let me give you a hint. Remember that the stress is actually equals to the principal times the principal value times spectral directions. So now if I take a partial derivative of the stress with corresponding to the principal stress corresponding to the stress tensor, what would you get? So by definitions, what we will have is that the partial derivative of the stress eigenvalues with respect to the stress tensor, it just gives you back the spectral directions. Okay? So this is a great advantage because once I substitute it there, then what I have is a very simple term, the stress gradient, the original stress gradient, which is actually, I would argue that it's not easy to compute or expensive to compute. It's simply FA NA times NA. Okay, now this become a very cheap calculation. Do you see why? Because I actually just need to do a scalar partial derivative of this. This is simply equal to the stress with respect to the eigenvalue. Okay. And what is n? I already know what is n, isn't it? N is the spectral directions of the stress, right? Okay. So do you remember what is the elastoplastic tensor in our previous lecture? Why do we need to compute this? Is that I want to write the Rita mapping, and the reason I need to write the Rita mapping is that I want to update the stress, right? So this also gives us an opportunity to write the elastoplastic constitutive operator in spectral form. And let's say that I have a passing flow directions now lambda dot equals to the, let me try to generalizing it so that it's actually equals to, so the passing string rate is actually equals to lambda dot of potential flow. Okay, so E is actually equal to a potential. And what we have in the if you want to write the elastoplastic tensor in the spectral form would be equal to CE minus 1 divided by X, which we talked about it in the previous lecture. Okay, so this is expressions, and if we remember what we talked about in the previous case, what we will have is that we will have something that look like the elasticity tensor, but in this case we will have A, E, P, A, B, and A times N, B. And the second term, the spin term, interestingly, is identical to the elastic counterpart. Okay, why is that? Because the spin term is actually independent of the constitutive response is on when you actually fixing the eigenvalues of the stress and strain. What happened to the spin? Eigenvalue of the second term come from when you fix the principal value of the stress and the principal value of the elastic strain. What happened to the what is the change of the tangents corresponding to the change of the directions? And actually, the most important thing is this term. Okay, if you look at the elastoplastic tensor, what is this? They are actually written. If you recall what happened to the elasticity, we only have two components for the A and B. For the elastoplastic tensor, the tangent term is only equal to this. Okay, so what are those numbers? So this is actually what we see before, the elastic component, and this C, F, and C, and then G, D are the partial derivative of the U stress corresponding to the principal directions of principal stress, and the partial potential corresponding to the principal directions. C and D are actually indexed for the major, intermediate, and minor principal stress. Okay, so far so good. Okay, so what should we do next? We have all those ingredients. In order to compute it, then what we actually want to do is to try to write the return mapping algorithm, right? Okay, so how do we do it? Okay, so let me try to compute this before we talk about a particular instance of the U surface, including the Camcray U surface, the Zucker-Prager U surface. Okay, so what we actually learned from J2 plasticity, the general equation is still valid. I will write the stress change in terms of the total stress minus the correction. Okay, but here I introduce a new concept, G. What is G? G is actually potentials. So in general, when we actually write the J2 plasticity, a lot of time we will use something called associative flow rule. Associative flow rule. what is associative flow rule is that we are assuming that the passing strain rate is equals to the lambda dot times the stress gradient. Okay, so the yield surface, the gradient of the yield surface, yield functions corresponding to the stress give you the idea is identical to the flow directions of the passing flow. In the non-associative flow rule, there are two types of the passing flow. Flow rule. One is actually the classical one, which rely on the potentials. So G is actually a function of the stress, but G in general are not equal to F unless they are associative flow rule, as you can see here. Okay, so what benefit do we get? Is that I can manipulate what kind of plastic deformation I will get, even though my yield surface could tell me otherwise, right? Does that make sense? Okay. In computer science, which actually usually have a better pay than us, I guess, they often use the Zuckerberg yield surface and have a J2 von Mises yield surface double as the plastic potential. Okay, so what is the consequence of that? The consequence of that is that your yielding is pressure sensitive, but the plastic deformation you get is always only have the rhetoric mode. There is no pressure mode, okay? So what will happen is that you cannot measure plastic dilatancy or plastic contractions, which mean that it doesn't work for soil in general. It can work in undrained state where the water is trapped, so that if approximately the entire material is incompressible. Okay, but there's a very common thing people use just for the simplicity. Okay, now go back to that. This is actually the general rule, and regardless of using we use the principal representation, they are still valid. Okay. Now I would need to convert it in an incremental form. So in other words, given sigma n, what is the sigma n plus 1? And I will write it like this. This is identical to what we have before. And so far, I haven't used any principal directions. Okay? So where is the sigma n? This is incremental form. The sigma n is hidden somewhere, right? Where is the sigma n? In which term? In here, or here? Yeah, in the child stress. Okay, so where the child stress, we obtain the child stress by assuming that the entire increment are completely elastic, which is actually a wrong assumption that we previously made, and then we rely on the last term to give us the corrections. Okay, so far so good. Okay, now, okay, so far you understand it. Now these equations is in spectral form. Okay, does that make sense? Coming from this term, and then the second term is just this. We're writing it in spectral form. Okay. Now notice that there is no spin term. Why is that? We need to use the spectral form. Okay, what is the spectral form for sigma n plus 1? What is it? Again. I think this lecture is like my finger going to a gym. I just keep using my finger muscle to keep writing stuff. And I simply expressing in spectral form for the stress strain curve. Again, they share the same directions. Okay, the charge, stress, and strain. Okay. So what happened? What should we do next? Important thing that we actually need to do is to consider the fact that we actually want to rewrite. So how do I write it? Okay, I need to write it. I simply need to write it out by substitutions. Okay, so that would be sigma A and A. Now again, the spectral form, if you follow the general rules, it's a substitution here. I just write m. I just don't want to keep writing the n anymore. Minus delta lambda. Okay, does that make sense? So this is very simple. I'm not making any change, right? Okay, so okay, I simply express the physical quality in the spectral form. So there is no when expressing the change, then I need to include the spin term. Now, there's also one thing that are very important, okay, from these equations is that if the underlying material is isotropic, then we can have a very important simplification is that n is actually equals to the m char A is actually equals to ma. Okay, the child principal directions and the actual principal directions are identical. So what it comes down to is something very simple. If I look at the individual eigenvalues of the stress, I will simply come up with this. Okay, again, GB is actually equal to the partial derivative of the Pasek potential correspond with respect to the principal stress. Okay, so do you see any benefit here? This equation, why is it significant? Okay. It looked pretty stupid, right? So why do I care about this? How many equations? Okay, let me ask you here, how many equations do I have? I write one equation, but actually how many equations am I expressing? So I have a equals to 1, a equals to 2, and a equals to 3, right? Okay, so if I want to write it out, I have 3 equations here. Okay, for the stress. And for the strain, I also have 3 equations. Okay, what is so magical of that is that, do you see any n or m in these equations? Okay, I don't see any of them, okay? So the magical part is that in order to write the return mapping algorithm, the eigenvalue is never involved in that revolutions. Okay, so this makes things much simpler. Okay, you see what I mean? Although I do actually need to deal with the spin when I actually want to obtain the elastoplastic tensor in the return mapping, I just deal with how the eigenvalue are changing. Okay, so this is actually pretty significant. Okay, and how many equations do I have here? For here I have 3 equations. And in order to write the return mapping algorithm, how many other equations do I need? It would depend on how many stuff I have for the system of equations, right? So in order to write a parasiticity model, let me go back to this. So what are the ingredients for the parasiticity model? Okay, I need to have elastic corrections, right? Elastoplastic. I need to have the stress update. What is the stress update? Is actually the stress n plus 1 equal to the n plus 1 child minus the corrections. Right? Okay. So this is one ingredient. What are the ingredients? I want f to be equal to 0. Okay? You see what I mean? So that implies that principles in the new case, remain equal to 0. Okay? Does that make sense? Okay? Does that make sense? Well, anyway, do you know why I write these second equations? Because in order to have the material continue to be yield, I need the material to fit the yield criteria, right? It has to meet the yield criteria. So this would be one of the ingredients I want to continue to enforce in my return mapping, right? Okay, what are the other things I want to actually enforce? So this, again, what is the name of it? It's actually called the consistency condition, right? Okay, what are the other things I want to do? Yeah, revolution of the U surface. How do I actually know how to perform the revolution of the U surface? In a more generic setting. In J2, what did I do? Do you remember? I actually write a functions. Do you remember what we did in J2? We actually write a function so that Kuiper is actually equal to is a function of epsilon p, right? What is Kuiper? Is the radius of the circle of the J2 in piping, right? Okay, or I can write it the back stress as some kind of functions of epsilon p. Okay, alpha is the back stress, which is actually the center of the circle. I can move the circle, and I need to provide it some governing law. Now, in the most general setting, I need another gradient, which is actually called the hardening law. Okay, in the most generic way, this is or sometimes it's also called kinetic equations. This is just give me a rule to write this. Of something, okay? Okay, some kind of hardening rule, okay? Or you can actually simply write that Kuiper minus Kuiper head functions equal to 0. Okay, so this is actually a function determined from experiment. most of the time. Usually you cannot derive it from first principle. Okay. Now, if I have these three type of ingredient and the material is isotropic, okay, let's say this hardening law is just a scalar hardening law. Okay, in general, the hardening law can be as simple as a scalar functions like J2 positivity isotropic hardening to something that have even higher dimension than the stress. Does that make sense? Okay. Like my former student, Professor Vanna's paper on the machine learning positivity, the hardening law has 16 dimensions. Okay, so this is much higher than the stress. Okay, now but in general, why do I need to write that? It's because I need to write the return mapping. Okay. Now here I want to use an interesting trick, and what would be that interesting trick is that I actually want to obtain this. I want to actually obtain the I want to rewrite that equations into functions of string. Okay, so if you want to write it as a function of string, what should I do? Actually, more accurately, I want to write it as a function of elastic string. So what should I do? I can simply write epsilon e n plus 1 equal to c e minus 1 double dot sigma n plus 1. Does that make sense? Okay, so if I write it in spectral form, then what would I get? Okay, what would I get? So I would get something like this. Okay, I would have the I would simply have the epsilon n plus 1 minus epsilon 1 plus delta lambda g1 equal to 0. Okay, and then I can actually substitute this into here. So if for convenience, I would call this a B matrix. Okay, with individual component, maybe I would call it B matrix. And eventually, what I would actually have is that I would have a system of equations that are coming from these three ingredients. Okay, and what are they? I would actually call this L, which is actually tell us how the hardening specific way, so that this minus this equation equal to 0. So when this L is taking a derivative with respect to Kuiper, this actually give me 1. Okay, you see what I mean? This is just the it will be the residual of the return mapping everything. Okay, it would be a vector that as a function of sigma 1, sigma 2, sigma 3, delta lambda, and a k. Okay, and if I write it out, I would actually have the form that look like this. The first term would be corresponding to what? It would be corresponding to E1J minus 1 plus delta 1 G1. Okay, what is G1? Again, G1 is the partial derivative corresponding to the major principal stress. Okay, now this is a 1 the index 1 is here, 1 is here, 1 is here. Okay, what is this? This is just elastic stress update, right? With the corrections. What is the second equations? Maybe I use the same color, sigma E. Okay, what should I write here? I just write 2 here, 2 here, 2. Okay. And then what is the last equations? I guess the same, right? I just write 3 here, 3 here, 3. I won't write anything. Okay, you know the form is identical. I don't want to torture you. Okay. And what else should I write? I should write f equal to 0, right? So I simply need to substitute sigma. I just put it here. Why is that? It's a residual. It's supposed to equal to 0 if it's correct, right? If it's not correct, then I can use the Newton raption to make it, to guide it to make it correct, right? Okay. And what else? If I have perfect plasticity, that's all I have. Okay? Just like J2 plasticity, I just need to put the elastic corrector equations as and the f equal to 0 equations into a system of equations, and then I solve that problem, then I would actually have the solutions, right? Okay, now, but I want to make the model more generalized. Then I will have a Harding law, and then how the internal variable involved, and I will call it L. Okay, so this is a residual. Again, this is the Harding law. This is actually from the consistency equations. And these 3 are just the elasticity with corrections. Okay? Now I have this system of equations in my return mapping, and then I want to find the solutions. Okay, so to actually obtain the stress update, I simply need to solve this. Okay, so what does that solving this residual mean? So solve in this particular context is an English word that means find sigma 1, sigma 2, sigma 3, delta lambda, k, n plus 1. Such that r equal to 0. Okay, that vector equal to 0. Okay? So how do we do that? Okay, I have a system of equations. Okay, unfortunately, one thing is that the U surface is not linear. Okay, it's not a linear function. Okay, it could be a sigma 1 minus sigma 3 square plus something, blah, 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 blah. It's not linear, right? So I cannot directly solving that equations with some ax equal to b, right? Okay, what are the choice I have? We have 1, 2, 3, 4, 5, isn't it? Isn't it? 1 equation, 1 unknown. So I have 5 equation, I have 5 unknown, right? Is it? Okay, is it? So this is clearly 1 equation. This is clearly 1 equation. This is clearly 1. Is this 1 equations? This is, of course, is 1 equations. It's a U functions is a scalar, right? So a scalar give you only 1 equations. How about this? This could be 1 equation, or it could be 1,000 equation. I don't know. Depends on what is the rule. But for the argument's sake, let's say I just have 1. I actually want to write the L in a very clear way. What should I do? Okay, I can use the Newton-Raphson. Okay, so I can use the Newton-Raphson to solve the problem. Actually, I just charged my laptop in the right amount is 9%. So by the time it go to 0, I think we can go home. Okay, so how do I use the Newton-Raphson? What is the necessary ingredient for Newton-Raphson? Let's reconsider the 1D problem, right? Okay, so how many of you already know what is the Newton-Raphson? Okay, let me repeat one more time because I really enjoy repeating that story multiple times, even though nobody is interested. So, okay, so this is a residual. Okay, this is the x. Okay, sorry, this is a residual. The y-axis is a residual. Okay, that are actually a function of x. Okay, I want to find this point where residual equal to 0. Okay, but my residual function itself is not linear, right? Okay, so I don't know how to find it. If it's linear, it's easy, right? So y equals to ax plus b, then how do I find y equal to 0? Okay, I just solve it, right? Okay, but how do I do it here? Okay, so I want you to think about it geometrically. This equation I presume is very complicated. I don't want to deal with it directly, but I can pick a point randomly, okay? Maybe starting here, okay? So what should I do next? Newton. So who actually raised your hand before? What should I do? I just put a point as the initial guess, and then I find out that, so x1, and then I find out that our x1 is not equal to 0, okay? So our x1 is clearly not the solution, so what should I do next?
Find another next guess.
So how do I find the next guess? This is a good question. Huh?
Tangent.
Tangent, okay. So I actually create a simpler version of that nonlinear equations. I compute the tangent of it, create a linear version of it that only work locally. Okay, and then I solve this problem. By solving it, I mean finding in this right equation where is the x equal to 0, and then I get this point, right? Now, this is a solution for the linearized equation, but not the actual solutions that are nonlinear. So what should I do? I just substitute it back into that equation, right? Okay, so what is the metric here? I kind of get closer, right? Okay, why do I get closer?
You don't know if the residual is closer to 0.
Yeah, but also it depends on the shape of the function. It's actually a convex shape, so you kind of have the benefit if I have a function that look like this. Okay, you may or may not able to do it. Depends on where you start. Okay, you understand what I mean? Or function that look like this. Okay, you will be in big trouble. Okay, now but here, how do I do it in multiple dimensions? Okay, in the multiple dimensions, let's say this is no longer for residual that depends on one variable. You can visualizing it as a curve in the 2D, right? Let's just increasing it by one dimensions, shall we? Okay, if I have a two variable, okay, what would be the residual function look like? It will look like a surface, right? Okay, I don't know how to draw it in. Now, let's say I want to determine R, and R will depend on X and Y, okay? Okay, so I have an X function, I have a Y functions, I have some kind of shape. I don't know how to draw it in a way that actually show that. This is X, this is Y, this is a residual, X, Y. Okay, I have some kind of surface. Okay, so what should I do? I still make a point, right? I still make a guess at some point in the surface. Okay, and what should I do next? I still obtain the tangent, right? Okay, but what is the difference between this tangent and the previous tangent?
High dimensions.
Yeah, exactly. Previously, the tangent only have one scalar, so basically the tangent and the derivative are the same thing, right? Here, what is the difference? Okay, your residual is a surface. What is your tangent? Your tangent is not a line, right? Isn't it? What is your tangent? The tangent is a plane, right? Okay, it's flat plane that are actually, if you look at different or two orthogonal directions, they actually share the derivative of it is actually the base vector. That's the definition of the tangent. Okay, so how to construct this? How to mathematically represent this? How do you actually create a flat surface? What is the necessary ingredient? I need two orthogonal vector so that I create a flat surface, right? Okay, how do I find those orthogonal vector? Exactly. So if you look at it clearly, you will see that this is just x and y. Okay, once I have the x and y, I span it, I will obtain a surface. Okay, isn't it? No, so now in the I'm just showing it in 2 dimensions. How about in this case, how many dimensions do we? What will happen? Okay, I need to find the tangents, and then I was saying that what happened to here is that I would go through with that tangent, and then I'm marching to delta x, so that I reach the new zero, right? Okay, so translate into multi-dimensions. What I actually want to obtain is actually the tangents, which I call it a delta x equal to the Rx k. Okay, so a here is the tangent in multiple dimensions. And this tangent is actually obtained by what? Is simply the partial derivative of it with respect to x, and I need to define x. What is x? X is actually just the individual component that I need to update. Okay, I need to update the partial multiplier, delta lambda. I need to update sigma 1, sigma 2, sigma 3, and I need to update Kuiper, right? Now, in this particular case, I'm interested in create a string-based update, and that AK would be equals to B11, B12, B13, blah, 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 blah. So this would be a 3x3 matrix times the delta lambda stress corrections. G1, G2, G3. Sorry, need to because right Arlen law. Try it again. AK would be equals to, this one is just B IJ, and then this would obtain the 3x3 matrix and have delta K partial derivative of G with respect to the internal variable times G1 to delta lambda G3 K G3. Okay, this is the stress correction part, and then I would actually have this equal to 1 and this one equals to L with respect to delta lambda, and this part would be the gradient with respect to the hardening law. with the principal stress. Or I may simply write, for simplicity, L1, L2, and L3. And the last one is very simple, just the stress gradient in the principal directions. And the stress and the U surface change corresponding to the tangent and zero. Now, this 1 and 0 are actually triggered by a very specific meaning, very specific order, is because I write the x in terms of the eigenvalues of the stress, followed by the Hardy's law, followed by the Pasek string. Okay, why is this equal to 1? Why is it equal to 1 here? Okay, so with that, then and Bij, let me define the detail, is simply equals to Ae Ij minus 1 plus maybe I used to. Okay. Which actually, so this A term is also, they are called the local Jacobian because each of the gaseous point in a finite element would have its own Jacobian, and they're different than the Jacobian or the tangents of the entire residual of the finite element. Okay, for a nonlinear finite element Coke, you have a global Jacobian corresponding to the relationship between the global residual coming from the balance law with respect to the displacement, and a local Jacobian that are corresponding to the local stress strain update. Okay, so this is actually called the local Jacobian. If you actually look at the textbook in books 4.1, you would see the spectral decompositions that are actually nicely summarized into the box. Now, if you actually want to complete your final using writing the partial sensitive positivity, what you actually need to do is to implement a box 4.1